the pushing force of the upper arm bone on the lower, FH on the lower arm bone. Okay, so let's draw the free body diagram. The free body diagram is like that, the same thing. Okay? This is the free body diagram. Okay, so you have the load, which is 490 newtons also. So you have 490 newtons, and then the arm, the weight of the arm is still the same. So that 24.5 newtons. So at the center of gravity, at the geometric center of your structure, so this is 24.5 newtons. Okay. Then you have the biceps. The biceps now are perpendicular. The biceps now here are perpendicular. It's no longer at an angle like that. It's perpendicular. So you have the force here. So this is FB. Okay. Still acting. Still the application point is still 4 centimeters from the elbow joint. So this is 4 centimeters. Okay. So you have there 4 centimeters, 4 cm. Okay. That's 4 centimeters. Then you have the pushing force. Okay, so the pushing force now is acting this way. So this is FH, it's perpendicular. Okay, it's like that. So the humerus is actually directly pushing on the elbow joint at 90 degrees. This is simpler. That's simpler there, right? So the fulcrum, the actual fulcrum is here, but you can choose any pivot point. Where do you want us to have our mathematical pivot point? Where do you want it to be?
Center of gravity.
Center of gravity. Okay. Who was that? Aaron. Okay. Let's here. At the center of gravity. Okay. Now, the same thing. First, the force conditions. Up equals down, right equals left. Right equals left. Right equals left. You will see there are no forces acting horizontal. So we don't need to use this. We don't need to invoke this because there are no forces acting to the horizontally. Okay, so this, no need. The other one, up equals down. Forces up should be equal to forces down. Forces up is just this, FB. Okay, FB equals to downward forces. What are the downward forces? The weight of the arm and the weight of the load. And also the FH. This FH is directly acting downward now. So this will be FH plus 24.5 plus 490. Right? So this will be FB is equal to FH plus 514 plus 514.5. This is equation 1. Okay, that's equation 1. Now, the torque condition, and Aaron wants to make our life difficult by choosing the pivot point here. You know why it's more difficult? Because now FH and FB are both in the torque equation. You now have two unknowns, but it's okay. It's okay. It really doesn't matter. So, for the torque condition, okay, counterclockwise torque should be equal to clockwise torque. Here, if our pivot point is still at the CG, okay, the pivot point is at the center of gravity. If our pivot point is there, it's as if that you hinge. It's the structure here is hinged at the center, so it rotates this way, clockwise, counterclockwise, and clockwise. Okay, so counterclockwise, for counterclockwise, what's the force that's producing counterclockwise rotation if the structure is hinged there? If the structure here is pivot, has a pivot point there, it's equal to, for counterclockwise, it will be just FH, right? FH produces counterclockwise rotation. Right? If you look at it, it rotates counterclockwise. So it will be equal to FH, right? FH times the lever arm. The lever arm from the line of application to the pivot point. The pivot point is like the center of gravity. All of this is 4T. All of this is 4T. So you have this is 40 centimeters. This half of 40 is 20. Right? Because this is at the center of the geometric center of the structure. So this will be 20 times 20. So that's the counterclockwise torque. Let's now go to the clockwise torque. The forces producing clockwise rotation would be what? Would be this, it's clockwise, and this, clockwise. See it? Is it? Yeah. So you have this. What about this? What about this 24.5 Newton? Will it contribute any torque? It won't, because it's passing at the pivot point. The lever arm is 0. So there's no torque. There's no torque contributed by the weight, by 24.5 Newton, if your pivot point is there.
So you wouldn't add it in your old?
No, don't include that. Effectively, you have killed, you have murdered this 24.5 Newton force. Okay? You have murdered that. It's no longer there. Okay, so this is now equal to 490 times the lever arm. The lever arm is just 20, right? It's also 20. It's equal to 20 plus this one here, FB times the lever arm. If this is 20 and this is 4, this should be 20 minus 4, 16. So this will be 16. Okay, so there you have the second equation. Or let me just rearrange this. 20 FH is equal to 490 times 20 is how much? 9800 is 9800 plus 16 FB. This is equation 2. Ha! Finish! Right? You have one equation, another equation. The equation 1 there, you have already isolated FB. FB is expressed in terms of FH. Plug that there. You will reduce the equation into only one unknown. Okay, so you have 20 times FH is equal to 9800 plus 16 FB. This is FB. You're plugging this into 2. You're plugging this thing into here. 16 times FH plus 514.5. So see, you now have just one unknown where you can now calculate for FH. So you have 20 FH is equal to 9800 plus 16 FH plus 16 times that price. 16 times 514.5. 8,232. Okay? So 20 F transposing 16 to the other side will be minus 20 minus 16 gives you 4 FH, right, is equal now to 9800 plus 8232, right? 9,800 plus 8232.
18,032.
1832. So FH is equal to 1832 divided by 4. How much?
It's 18,032.
1832. This one here?
Yeah.
18,000.
Ah, 18,000. Sorry, I'm stupid. 18,032 divided by 4. How much is that?
4,500.
4,508 newtons. So you have FH. Let's calculate for FB. Yeah, this is FB. Once you know FH, you can calculate for FB. FB is just equal to FH. FH is 4. So you plug this value here. So you have 4508 plus 514.5. This gives you how much?
5,022.5.
5,022.5 newtons. So you have calculated for FB and FH. Now look at the previous example where the muscle was at an angle. What was FB? Compare with angled biceps. What's FB? FB is equal to 5,800. FB is 5,800, which is greater than that. It's greater by about 800 newtons. 800 newtons is about 200 pounds. So 200 pounds is a large force. So it's effectively reduced the strain on your muscle if you bring the load closer to you. Don't walk around like this. Walk when you bring the load closer to you. Not like that. I remember when I was still in Saudi Arabia, even the guys, they walk around with their